Hello, welcome again. So the last time we talked about the crystal structure of solid materials, and we talked about chapter 3. So in chapter 3 we're going to see the structure of crystalline solids. I make mention of this, and then we talked about how the spots in the diffraction pattern are produced. If you remember, we talked about that. I'm going to show you what I mean by that. If you take a look at this here, this is the picture I showed in the last video when we use the diffraction meter. So here clearly you can see, I can use the pointer. Here is the X-ray source from yesterday, what we talked about, and here is the incident, the lead screen. That's the lead screen, and here is the incident beam. Then we have the single crystal, the diffracted beam, and the photographic plate. So this is the photographic plate that we use, the Lowry photograph, and this is the X-ray source. So if we have an X-ray, you penetrate it through this lead screen, then we make a hole wherein the X-ray can penetrate, and we can have any material here. This can be a single crystal, this is a magnesium material. It can also be a gold, it can be diamond material, and then when you penetrate it, then you can see this dot. This dot, we make it bigger here. So you can clearly see from this picture, here, this is the big dot. This big dot here is the 001 plane. So every dot you are seeing is a plane within the single crystal. So, however, you can see how the dots are arranged. So if you take a closer look at this dot, you can see there is a dot here, dot here, dot here, dot here. So these dots, when we combine them, then we can have a crystalline structure. We can have something like this. So this dot here is what gives us this single crystal. So this is the total. So this is how the atoms are packed within the crystalline structure of the materials. And you can see this big dot, this 001 direction, and this is the 001 plane of atoms. However, this bigger dot, this one, corresponds to this 0 here, this 001 direction. So this is a magnesium. A magnesium is brittle, so that means you can see we break the magnesium there with this 001 plate here, and that is here, this one is the 001 direction. So here is a typical example of a material that we can use to make a magnesium. This is a lightweight automobile wheel made of magnesium. So briefly, that's what we talked about in my previous video. So I advise you, if you didn't see that video, go ahead and check out that video. So today we're going to come and look at this. Why study the structure of crystalline solids? Why do we study crystalline solids in materials? So basically, there are many reasons why we should study crystalline solids. So one of the main reasons why we should study crystalline solids is that because we know that the properties of materials are dependent on the structure of these materials. So, for example, if we have a magnesium crystal structure, so this magnesium, it is brittle in nature. What does that mean? That means that this magnesium can easily fracture. If you go back previously, we look at this video here, I make it a little bit bigger. So you can see that it is brittle. It's very easy to fracture this magnesium. You can break it. However, if we have another crystal material, let's say we use gold in this single crystal, so instead of magnesium we use gold, then we can see that this one, it is much more stronger comparing to magnesium. So that's why we want to study the crystal structure of materials, because if we understand the crystal structures of materials, we can able to make materials, we can able to manipulate materials. So that's one of the reasons. So, and we also talked about previously in my previous videos about plastic, ceramics, as well as composite materials and metallic materials. However, all these materials, they have different crystalline structures. So, for example, if we have polymers, polymers can be crystalline and non-crystalline materials. So, sometimes when these polymers are crystalline, their structure, the way how the atoms are arranged, because crystalline materials are materials that the atoms are arranged in a repetitive order in a long period. Where in non-crystalline materials, these are randomly arranged. The atoms are randomly arranged within the material. So if we have a polymer that is non-crystalline, a typical example will be a glass or a plastic. A typical example will be like this. This is a polymer material, and this polymer material is transparent, meaning you can see through it. This is because of the randomness arrangement of the atoms. The atoms are randomly arranged. But however, if you have another plastic material, this is plastic, but this is, you cannot see through this, but you can see through this. So that means this material, the atoms within this material is arranged in an orderly manner. So that's one reason why we have to understand the structures of materials, because if we understand the structures of materials, we can able to arrange these atoms. So you can see that we have many reasons why we should study material structures, because these material structures influence the properties. So why we study? What are the learning objectives after studying this material? So from here you can clearly see this is a pattern. This here, this is a pattern that you have to see. So this is a mathematically pattern. So after the being reflected, these incident beams, these diffracted beams have diffracted, we have this pattern. With this pattern right now, you cannot do anything much. But however, mathematically, we can look at this pattern and able to determine the structure of these materials. For example, you can see these dots. These dots are plates of atoms. So now I'm going to show you how we can transfer this dot. These dots are like this. We saw these dots. We saw some like this. We have so many dots. So now if we connect these dots together, we can connect them. Okay, then we can my drawing is really poor. Okay, so what you see here, this is the dot we connected, and these connections here, these are the atomic bonding. These are the atomic bonding between atoms. These are planes. These are the bonding between these atoms. So what you can see how many dots? 1, 2, 3, 4, 5, 6. So this is called a hexagonal. Oh, let me see. Maybe let me take another pen. So we can have a HCP. HCP meaning, from the last video we talked about it. It means hexagonal, closed, packed crystal structure. Okay, this is a hexagonal closed packed crystal structure. So what this is telling us, that the structure, if you look at the microscopic details of the material, you can see this structure. So every material, whether it be magnesium, chromium, and other materials that have this crystal structure, they have similar properties. So the only way you can able to understand this mathematically is when you are able to connect these dots. So that's what we are doing. I bring you. So that's what we are doing right now. So you can see this is the hexagonal closed packed crystal structure. So with this dot, we can have this direction. So now here is another crystal structure. So this is also what we call, in metals we have what we call different metallic crystal structures. We have the FCC, like I make mention of here. We have the BCC, we have the HCP, and all these have their meanings. So next, in my next video, what we're going to do, we're going to see these learning objectives. Why do we study crystalline structure? So this is just a reason of why we study. And we're going to see when we arrange this in these diagrams. If we want to describe an atom at this point, what are we going to do? How are we going to describe that atom in that particular point? So then we need what we call unit cells. So we're going to describe the difference in atomic and molecular between crystalline and non-crystalline materials. What are crystalline materials and what are non-crystalline materials? Then we're going to draw a unit cell for what we call the face-centered, body-centered, and hexagonal for metals. And then we're going to derive the relationship between unit cell edge length and atomic radius. And then we're going to compute the density for materials, how dense these points are, how dense are these materials. For example, here you can clearly see at this point, how can you determine the computation density of these materials? So these are very important. So that's why we need the mathematics. So we need to compute the atomic radius and the densities in order for us to be able to determine density. And we're going to use, how are we going to use this in terms of directions and planes? Okay, so we're going to use what we call the Miller indices. The Miller indices is the method that we can use to determine the directions and planes within a material structure. And we're going to see how we can describe the hexagonal close-back stacking, how these atoms are stacked. For example, you can clearly see here how these atoms are stacked within this material. So we're going to clearly see that, and we're going to distinguish between what we call crystalline materials and polycrystalline materials. From the word poly, here, from the word poly meaning many. So if you have a crystalline material, a single crystal, meaning that it only have one structure that is repeating throughout. So if it have an HCP structure throughout the material, you only have an HCP structure. But when we say polycrystalline, that means it have many structures. So it can have a hexagonal, it can have a face-centered, it can have a body-centered. But we're going to see all these terminologies and what they mean. And then finally, we're going to define what we call isotropy and anisotropy. These are just nouns. And isotropy meaning that in terms of properties, that it can allow these materials, electricity, to flow within one direction. And an anisotropy material is wherein the material will not allow electron or electricity to flow within that material. So basically today what we have covered these 2 points. We have covered, yesterday in my previous video, we covered this. Today we have covered why we study crystalline solid materials, and we have covered the learning objectives. So next we're going to see the fundamental concept, unit cells, and we continue from there. So watch out for my next videos. Until then, I say have a great day.